In this video, we're going to continue our discussion about linear analysis, and we're going to really, again, continue to focus on linear functions. So I believe we left off with the rate of change between 2 points. So the rate of change is really just a fancy way of saying the slope between 2 points, and it's pretty easy to do that. So you got 2 points, x1, comma f of x1, and x2, comma f of x2. And remember, a lot of you probably used to call this x and y, but y we're now calling f of x. So if you take x and plug it into the function, you get the output, which is y. So the rate of change between the 2 points is simply subtracting your outputs or your y coordinates on top, f of x2 minus f of x1, divided by the subtraction of your x coordinates, x2 minus x1. Really, really simple to do. So here's a basic, really simple example with a linear function. So we have a linear function f of x equals 1/3 x plus 5. And a question might say, find the average rate of change between x equals negative 9 and x equals 3. So it's really simple to do. The first thing you got to do is find the corresponding y coordinates, right? So plug negative 9 into the function to get the output, plug 3 into the function to get the output. So generate the 2 points. Then all I got to do is follow the formula that you all know and love. So first I plugged negative 9 in and I got 2. Hopefully you agree with that. I plugged in 3 and I got 6. Then it's a matter of just following the rate of change formula. 6 minus 2, those are my y coordinates on top, is 4. 3 minus negative 9, 2 negatives in a row makes a positive, so 3 plus 9 turns into 12, and 4/12 reduces to 1/3. Now that should come to no surprise, because if you look back at our linear function, we already knew the slope was 1/3, and this is a really simple idea. Linear functions have the same rate of change between any 2 points. That's why when we look at a graph of a linear function, we recognize that it has a constant rate of change. It doesn't matter what 2 points you choose, the rate of change between them will always be the same. That might not be true for other functions, but for linear functions, it's always true. So we say they have a constant rate of change, i.e. a rate of change or slope that is always the same. All right, next up, let's talk about solutions, x-intercepts, and zeros. These 3 things are all the exact same. They are where the graph crosses the x-axis. These points are known as solutions. So like really, really important. The key thing is that y equals 0. The function equals 0. When you're trying to figure out where you cross the x-axis, you know that for sure the output, the y value, is 0. So to find solutions by having a graph, well, you just kind of look at the graph. And to find solutions algebraically to give a really nice exact answer, you simply set f of x equal to 0, aka y, and then you solve for x. And hopefully you guys know how to solve. Not too bad, right? So know how to do both. It's nice and simple. So here's a pretty easy example. So we have a graph. Now, if I were to tell you to look at this graph, and I have the function written here, but imagine that the function was not written there, and you simply had to find the solution. Well, you'd say, well, it looks to be a little bit less than 1. 0.9, 0.8, 0.7, 0.75, 0.81, 0.86. It's just a little bit less than 1, so I can't be exact. Of course, in the world of math, we love to be exact. So if we actually have the function, that is how we can be exact. So all we have to do is turn that f of x into a 0 and solve. Look how easy that is. So step 1 right here was turning the f of x into a 0. Nice and simple there. I then subtracted 2 from both sides, getting these 2's on the right to cancel out, and creating 0 minus 2 is negative 2. Then, getting rid of fractions for some kids is difficult, but hopefully for you guys it's going to be easy. Technically, we are multiplying right there, right? So you would say, well, the opposite of multiply is to divide. So we're going to divide both sides by negative 7/3. But every one of you should know that the opposite of dividing by negative 7/3 is to multiply by the reciprocal. So instead of dividing, I'm going to multiply the negative 2 by the reciprocal negative 3/7. It stays negative. Some kids will turn it into a positive. Don't do that. It's just the reciprocal, so just flip it over. So instead of negative 7/3, we're multiplying by negative 3/7. And then that's pretty easy to do, right? Remember, you do not need a common denominator to multiply, so we could treat the negative 2 as negative 2 over 1. Negative 2 times negative 3 is positive 6. 1 times 7 is 7. There's our answer, 6/7. Now, that is exact. 6/7 is a rational number, obviously. It is approximately 0.857. So if we look back at that graph, where originally we were like, I'm not quite sure exactly what that is. It's just a little bit less than 1. Now we know that it's exactly 0.857. All right, this next topic and final topic for this video is actually a really big topic that I'm going to kind of make simple right now, but in the future we'll definitely do a lot more explaining with it. So continuity. So basically, in layman's terms, without any ton of math definitions or anything like that, if you are continuous at a point, it means that you could draw right through that point nice and smooth, right? So if we have an XY axis and here is a X value A, if my graph passes right through A without anything happening, without any hiccups. Now at this point, you might be like, well, what hiccups could occur? Well, we're obviously going to learn some of those. But if you can draw through A, so maybe some kids will make like a dotted line through A. If your function goes through that X value of A, nice and smooth with no issues, we say it's continuous. So to be continuous, to efficient, now here comes the actual math of it all, right? The definition. To have continuity at an X value, right? First, a point must exist at that X value. So if I want to prove that I'm continuous when X equals A, when that looks like a 9, A, I have to be able to plug A into the function and get an answer, get something, right? I have to get a value. I can't get DNE. I can't get bleh, divide by 0 or square root of a negative number. Those things would be like bleh, nothing. I need to get a number. Now, the second thing, and again, if you look at my graph right here, there does appear to be a point right there. Now, the second and third thing is this. As X approaches the value in question from both sides, the function is approaching that same value. So here's what we mean by that, right? As we think about the function getting closer and the function getting closer. So as we approach A from the left and the right need to be coming together. And you might be like, well, what would an example? Doesn't that always happen? Well, no. Give me some moments. We're going to look at some pretty cool things where that doesn't happen. But just to try to make sure you guys understand the definition, the left and the right side need to be coming together. Now, to explain that, we actually use limits. So we say the limit as X approaches A of the function, it needs to exist. Again, we need to get a number there. We need to get a value. So again, remember, limits are asking you about approaching a value instead of what happens when we get there. If I tell you what happens at A, that's where you plug A into the function and you find out what happens at A, right? That's simple. But in limits, saying what's happening as we approach A. What's happening as we approach A from the left side and from the right side. And we need the two sides of A to be coming together. And the third piece that makes it all tie in is that all of these values have to be the same, meaning that where the point exists, this value right here, and where the limit exists, which is asking you what happens as we approach from both sides, those two values, I just put number signs there, maybe a V for value, right? Those two values have to be the same. Otherwise, you are not continuous. And trust me, it's the first time you're learning about continuity for the most part. So when we'll look at plenty more examples where we see all these weird hiccups that could occur, and then you'll start seeing how these rules actually do make a ton of sense. But let's just look at one example really quickly for you to kind of see what I'm talking about here. So here's a nice, simple linear function, right? Super boring. The domain is negative infinity to infinity. This particular one is obviously a negative slope, so it's always decreasing. There's no min, there's no max. It's kind of boring. There's just not a whole lot to talk about. So one thing we could ask you is what happens when X equals 3? Is the function continuous at X equals 3? So what I kind of tell some kids to do is draw a dotted line down X equals 3. And look, where does your dotted line cross the graph? You say, okay, there it is right there, cross the graph right there. So now there's three things we have to check for continuity. First, we have to make sure that when we plug 3 into the function, we get something out. And you guys know how to read a graph. If I plug 3 into this function, looks pretty clear that I get -5. Makes sense, right? Then we have to talk about that limit. We have to say, all right, what happens as we approach from the left side and the right side, right? So we're thinking about that red dotted line, and we need to approach it from both sides. And we're saying, hey, as we approach that dotted red line, like I think about if I'm walking on the function, like maybe I'm a little person here and I'm like walking on the function, and I'm approaching the dotted line. and maybe I'm another person on this side and I'm approaching the dotted line. So again, the mathematical explanation for this people walking that I'm trying to explain here is a limit, right? We're saying, hey, what is the limit as x approaches 3? For this function, where is the graph going? As we approach from the left side, where am I going? As we approach from the right side, where's the graph going? And guess what? -5 is where it's going. So again, -5 equals -5. So where the function is at and where the limit is at need to be the same. When that happens, it means you're nice and continuous. So again, here's kind of like more evidence of this. By the way, this function was the same one we saw a couple moments ago, -7/3 plus 2. So again, I'm just trying to prove to you that, step 1, plug 3 in. Plug 3 in, you get -5. Nice, beautiful point right there. Then look at the left side. Here's the left side. Here's the right side. Their two sides are coming together at -5. So the limit exists at -5. And then the best part is that where the point is, -5, is equal to where the limit is, -5. And that is how we have continuity. Now, if you're saying, like, wait a minute, this seems like the silliest explanation for the simplest thing. So in the next video, we're going to look at some crazy functions, not that crazy, I guess, but some different types of functions where we could make these rules about continuity break down, and then we see how they actually fall apart, and we do not have continuity at certain points. Now, by the way, I just chose 3. I could have chosen a lot of points. Like I could have chosen, 1/2. Like I said, are we continuous at 1/2? And again, you would draw that line at 1/2 and you say, okay, is there a point at 1/2? Yep, it's right there. Left side, right side, do they come together at the same point? Yes, we have continuity. In fact, when you're at linear function, you are continuous everywhere. There are no issues with continuity. So why am I even talking about it? Because in a couple moments, we're going to see in a different video how we can create some situations where we break continuity. I can't wait to show you those. All right, that's it for this first video.